Hi and welcome to a lesson of real analysis. So today in class we will discuss about the supremum and infimum of the sets and bounded and unbounded sets. So we'll start with some theorems. That is the first one, supremum of a non-empty set S of a real number whenever it exists is unique. So in this theorem, we have to prove that if a set has a supremum, then it is unique. So let's start with the argument that if possible, we have K1 and K2 be two least upper bounds of set S. So we have chosen that there are two least upper bounds of the set. Since both are the least upper bounds, therefore they are the upper bounds as well. So by definition, we can say that if K1 is the suprema, that is the least upper bound, and K2 is the upper bound, then the least upper bound, that is K1, is less than or equal to all the upper bounds. So since K2 is also an upper bound, so K1 will be less than or equals to this upper bound. We call it equation 1. And again, if we choose K2 is suprema and K1 is the upper bound of S, then again, same is the situation for K2, that K2 is less than or equal to K1, because we choose that K2 is the least upper bound and K1 is the upper bound. So it will be less than or equals to K1. Therefore, if we combine these two statements, so K1 is less than equals to K2 and K2 is less than equals to K1, then there is only and only one condition, that is K1 will be equals to K2, right? That is the only possibility. So here we arrive the argument that K1 is equals to K2, hence the supremum or the least upper bound is unique. And again, for the infimum, same is the argument that if the infimum of a set exists, then it's unique, right? So again, we can take the same argument and we call that M1 and M2 are two possible greatest lower bounds of the set, that is the infimum. Is also called infimum of S, since both M1 and M2 are the infimums and therefore they are also the lower bounds of the set. So by the definition, we have that if M1 is the greatest lower bound, then it is greater than or equals to the other lower bounds. So we take M1 is greater than or equals to M2 and call it equation 1. Similarly, again, if M2 is the infimum and M1 is the lower bound, then M2 is greater than or equals to M1. And we combine both equations 1 and 2, then we get the result that M1 equals to M2. Therefore, the infimum, the infimum is unique. Infimum is unique. So we prove these results. Now we will take some problems that a set is said to be bounded. Okay, there's a definition that a set is said to be bounded if it is both bounded above and bounded below. So if both the infimum and supremum of the set exist, then we call it bounded set. So let's take an example of this set that is 1 over n such that n belongs to the natural numbers. We write this set. So the set is of this form: 1, 1 over 2, 1 over 3, 1 over 4, and so on. Therefore, the infimum of this set will be 0. As we have talked about this set a lot of times, we know the limit point of the set and we know where the set is going. And 0 will be the infimum of the set, but it does not belong to S. This 0 does not belong to the set because we are not saying that n equals to infinity, but we are saying that n is approaching to infinity. So when n is approaching to infinity, the numbers are going towards approaching towards 0, but 0 will not be the element of the set because we are not taking n equals to infinity here. And similarly, the supremum of the set is 1, the greatest element of the set is 1. Okay, now these are some questions that tell whether the sets are open, closed, both, or neither. Okay, let's talk about this set first. That is 3, 5 union the singleton 6. So 3 comma 5, this set, we have all the real numbers between 3 and 5, excluding 3 and 5, and then we are taking union with 6, that is the singleton set. So by the definition of the open set, first of all, we'll check if it's open. So this is an open interval. This is an open interval. So this is an open set. Union, this is a closed set. So it's a finite set. It's a closed set. It's a singleton element. So if we take the union, and okay, if we check for the neighborhood of each point in this interval 3 to 5, we will get the neighborhood for each point. But when we arrive here at this element, so we cannot get any neighborhood for this element that belongs to the set. So this set is not open. And for the closeness, again, the same argument, we have the definition that a set is closed if it contains all its limit points, but the limit points of the set are 3, 5. So the set does not include all its limit points. So the set is not closed as well, so it's neither. And for this one, we can see that this is a union of open intervals. So we know that the union of open sets, and these are open sets as well, because all open intervals are open sets. So the union of open intervals is open, therefore this set is open. And this one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 elements. So this is a finite set, and we know that finite set is always closed set. So this is closed. And this one, negative infinity to 0, this is open set. And this one here, 0 to 1. Again, this set is not open, but we can say that it's closed from the left and open from the right. And if we take the union of these sets, so we have, we can write it as from negative infinity to 1 combinedly, and we can open this set because it's continuation. This is negative infinity to 0, and then 0 is included here. So we can write this union as this thing, negative infinity to 1. So 0 is included in the set, and all other elements bigger than 0 are included till 1. So this set is now open. So this union is again open. And Z, that is a set of integer, and we know that it's like -5, -4, -3, 0, 1, 2, and so on. So it's a set of discrete elements. So this set is closed as well. How we can prove that this set is closed? So by the definition that the set is closed if and only if its complement is open. Okay, if we take the complement of the set Z, that is R minus Z, we are going to obtain the open intervals. So R minus Z, we will obtain open intervals like this: -5, -4 open, -4, -3 open, similarly like that. And if we go on, we have 0, 1, and then 1, 2 open, and you can see that these are open intervals. So R minus Z will be the union of these open intervals. So open intervals are open sets. So the union of arbitrary union of open set is open. Therefore, the complement of this set of integer is open. Therefore, the set itself is closed. And then if we talk about this set, negative infinity to 0, union 0 to 1. So the case here is the 0 is not included. 0 is not included, and from here it is closed. This is something different from this case that we discussed, because for this case, we said that we can write this as a single interval, that is negative infinity to 1, as this open interval, but we cannot write this as a single open interval, and therefore it's closed from one side. Therefore, it's not open because we cannot get the neighborhood of 1 if we want to obtain the neighborhood, so it's not open. And it will be neither closed because if we take the complement of this set, so it will not be open, right? Therefore, this set is neither open, neither closed. And again, for this set is a closed set because this is from negative infinity to 0 and union 0 to 1. So 0 is excluded here, but it's included here. So we can write this set as negative infinity to 1. So this set is a closed set. Okay, because from here we can just get a misconception that why this we are calling this set as closed, because this here is open, because this is coming from negative infinity, and negative infinity can never be closed. So it's coming from the negative infinity, and it's uh, closed from the side 1. And if we want to check that the limit points of this set, so the limit points of this set will be the set itself. So by that definition, that if set contains all its limit point, then it's closed. We can say that this set is closed because this set contains all its limit points. Okay, so the limit points of this set will also be negative infinity to 1, like this. So this is a closed set. Now this set R minus 1, 2, 3 is open set because again the complement of this set is a closed set, because the complement of this set will be minus R minus 1, 2, 3. So this R and R will cancel, so we'll get 1, 2, 3, which is a finite set, so it's closed. Therefore the complement is closed, therefore this set itself is open. And again, for 1 over n such that n belongs to natural numbers, this set is like 1, 1 over 2, 1 over 3, so on. And we can see that this set is neither open nor closed, because for openness, we should have all the neighborhood of every point in the set, but it's not the case, because if we want to take neighborhood around these points, for instance 1 over 2 or 1 over 3, so we cannot get an epsilon neighborhood. So this is not open, and again this is not closed, because we can see that the limit point of this set is 0. We already discussed in earlier classes, and that is not contained in the set. So 0 does not belong to the set, so the set does not contain all its limit point, therefore this is not closed set. So it's neither open, neither closed. And again, for this set, now this 0, that is the limit point, is included in the set. So we already know this is not open, but now because this 0, that is the limit point of the set, is included, so this set contains all the limit points, that is the only 1.0. So this set is again closed set by that definition. For rational numbers, again, rational numbers are neither open, neither closed, because for Q, we know that the rational numbers are not complete. So therefore, there are gaps between rational numbers. And we cannot say that this set is open, because there are gaps and we cannot find epsilon neighborhood for each element. So it's not closed or not open, and not closed as well, because it the complement of the rational numbers is not closed. And also the set does not, the limit points, all the limit points of this set are the real numbers. We know that the limit point of this set are the real numbers, but the real numbers are not contained in this set, so it's neither open, neither closed. And for this Q intersection 0, 1, again, it's neither open, neither closed, because of the same argument that we concluded here. This is neither open, neither closed. So these were some examples of the sets, open and closed sets. So now let's talk about one example. Find the infimum and supremum of the following sets. So we have a set m plus 1 over n such that mn belongs to the natural numbers. So the set will be like this, 1 plus 1 over 1, because m and n belongs to the natural. So first we can write this set in this way, 1 plus 1 over 1, then 1 plus 1 over 2, 1 plus 1 over 3, and so on. Then 2 plus 1 over 1, because this m is also from natural numbers, 2 plus 1 over 2, 2 plus 1 over 3, and so on. And then 3 plus 1 over 1, 3 plus 1 over 2, 3 plus 1 over 3, and so on. So it will move on and on. and m plus 1 over n, and like this. So the infimum, we can find the infimum of the set because the lowest element of this set will be 1, as we can see that for this particular set, if we go on and on like this, 1 plus 1 over 3 and so on, so eventually we are going to get uh, near 1. But this 1 does not belongs to the set, that cannot be belong to the set, because again that is the case that n is approaching infinity. It's not actually infinity. So 1 is the infimum of this set, and it's bounded below because supremum does not exist. We cannot find the largest element of the set. So supremum does not exist, and we cannot find, even not find the bound of the set. So it's not bounded above, so it's only bounded below, and the infimum is 1. Again, for this set, that is x belongs to the integers such that x squared is less than equals to 25. So the set will be like this from -5 to 5, and the set of integers, it's a finite set, so it's a closed set, and it's also bounded because the greatest lower bound we have -5, and least upper bound we have 5. So the infimum -5, supremum 5, and the set is bounded set. So example of a set that is closed but unbounded. So these sets Z, N, these are closed sets, but these are not bounded because the complements of these sets are open. So these are closed sets, but they are unbounded. Natural number is bounded below but not bounded above, and set of integers is neither bounded below neither bounded above. So they both are unbounded, but they are closed sets. So now we are going to prove a statement that says that prove that the set S uh, a to the power n such that n belongs to n is unbounded above if a is greater than 1. Okay, let's assume that let an is bounded above for a greater than 1, then M is the upper bound of the set. Okay, we know that if a set is bounded, then there exists an upper bound, and that is unique, such that for all x belongs to S, so every element of this set S will be equals to or less than this supremum M. Therefore, this implies that a power n is less than equals to m for all n. And then taking the natural log on both sides, we have ln an is less than equals to ln m. And since we are taking the natural log, but this a is greater than 1, so therefore the inequality will not be changed because this will always be positive, and both sides will be always positive. So n ln a, the property of log shifted n to the base, to the left side of the log, then ln n ln a is less than equals to ln m, and from here n is less than equals to ln m over ln a. So this n is natural number, and this will be some real number. This is a fraction, so this can be some real number. Therefore, since ln m over ln a belongs to the real numbers and n belongs to the naturals, so it contradicts the fact, that is the Archimedean's property, which says that for all x belongs to the real numbers, there exist natural numbers such that n is greater than x. But this says that n will be always less than or equals to this real number. Therefore, this is a contradiction, hence this is proved. Now we have one more proof, that is proof that a dot b is less than equals to the product of their mods. Therefore, we'll exploit the condition of the triangle inequality, that is mod of a minus b is greater than or equals to the difference of their individual mods. And again, we can square both sides. By squaring both sides and opening the formula a squared plus a squared minus a minus b whole squared, we have a squared minus 2ab plus b squared on the left, and mod a squared minus 2a mod a mod b plus mod b squared. So we'll obtain this here. this step, and then simple algebraic manipulation, subtracting a negative a square, negative b square on both sides. This will cancel this and this and this. We will left with this thing here. And when we multiply both sides by -1/2, because we are multiplying by the negative sign, the inequality will be changed, and we will get AB is less than equals to mod of A and mod of B. So that's all for today's class. We'll meet in the next class and we'll start talking about the sequences. Thanks for watching the lesson.